Mathematics can predict realities beyond human senses. The physicist Eugene Wigner once called this its unreasonable effectiveness, a profound link between abstract numbers and cosmic truth. By the end of this journey, you will understand how equations act as a prophetic language, unveiling everything from hidden dimensions to parallel worlds. We will explore how math foresaw entire planets, and why it might suggest our universe is just one of many. What does it truly mean for a simple equation to describe the fabric of existence? Long before telescopes pierced the night sky, humanity was already mapping the heavens with geometry. In the quiet depths of the Mediterranean Sea, a corroded bronze artifact now known as the Antimatter mechanism lay hidden for 2 millennia. This intricate device, a complex clockwork of gears and dials, was engineered to calculate the future positions of planets and the precise timing of lunar eclipses. It was a physical prophecy written in mathematics. This was not merely observation, it was prediction. A profound shift was occurring in the human relationship with the cosmos. The ancient Greeks, particularly thinkers like Pythagoras, saw numbers as something far more than counting tools. They believed numbers were the very essence of all things, the hidden architecture of reality itself. To them, the universe was fundamentally mathematical. Plato took this idea further, proposing that the world we perceive with our senses is just a dim shadow. The true reality, he argued, existed in a realm of perfect, eternal forms, and these forms were mathematical in nature. A circle drawn in sand is always imperfect, but the mathematical idea of a circle, with every point equidistant from the center, is perfect and absolute. This philosophical foundation transformed mathematics from a descriptive language into a predictive power. By applying geometric principles to the motions of celestial bodies, astronomers could announce an eclipse years before it darkened the sky. They were not just describing what they saw, they were reading from a cosmic script written in equations. This established a breathtaking precedent. Mathematics was not something humans invented, it was a universal pattern we had discovered. It was the key to unlocking truths hidden from our direct senses. So if a simple equation could foretell the dance of distant worlds, what other unseen realities, what other dimensions of existence, might be waiting for their numbers to be called? The serene clockwork of the solar system seemed to develop a glitch. For decades, the planet Uranus drifted from its predicted path, its orbit wobbling in a way that defied the elegant laws of Isaac Newton. Astronomers were baffled. Was the great Newton wrong, or was something else, something unseen, pulling at the distant world? The answer would not come from a better telescope, but from the tip of a pen. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently turned to the numbers. They treated Uranus' strange wobble not as a failure of physics, but as a clue. By meticulously calculating the gravitational perturbations, the tiny tugs from an unknown mass, they worked backwards. The equations became a celestial detective story, and the culprit was an eighth planet, hiding in the darkness. Le Verrier, with unwavering confidence in his calculations, declared the precise coordinates where this new world must be. He wrote to the Berlin Observatory, urging them to look. Imagine the scene on that September night in 1846. Astronomer Johann Gottfried Galle pointed his telescope to the spot Le Verrier's math had dictated. There, within a single degree of its predicted position, swam a faint blue disk, Neptune, a world revealed not by a lucky glance, but by pure, prophetic calculation. Le Verrier had famously stated that he saw the new planet in his numbers before anyone else saw it in the sky. This was more than a discovery, it was a revelation. Mathematics had proven it could sense a physical reality entirely beyond the reach of human senses, pulling a cosmic actor from the wings and onto the stage. If math could find a hidden planet, what else might it be sensing? tugging at the equations that describe our universe. The discovery of Neptune solidified a profound truth, that mathematics could reach into the void and pull out a world. Yet this was only a prelude to a far deeper revelation, one that would warp the very fabric of reality. A young patent clerk named Albert Einstein was consumed by a simple yet dizzying thought. What would it be like to ride alongside a beam of light? This mental journey led him to dismantle the absolute stage of space and time that Newton had built. His theories of relativity revealed a universe where space and time were woven together into a single, flexible fabric called spacetime. And gravity, that force which pulls an apple from a tree, was not a force at all. It was simply the curvature of this cosmic fabric caused by mass and energy. A planet orbits a star not because it is pulled by a mysterious force, but because it is following the natural curve, the dimple, that the star creates in spacetime, much like a marble rolling around a funnel. Einstein captured this radical idea in a set of beautifully concise field equations. These were not just descriptions, they were prophecies written in the language of tensors and geometry. They predicted that the path of light itself would be bent by gravity, a phenomenon called gravitational lensing. They also foretold the existence of objects so dense that their gravity would warp spacetime into a bottomless pit, a region from which not even light could escape. Einstein himself was initially skeptical of this last prediction, finding the idea of what we now call black holes too strange to be real. But the math was insistent. The ultimate test came during a total solar eclipse in 1919. As the moon blotted out the sun, astronomers led by Arthur Eddington measured the positions of stars near the sun's darkened limb. Their light, traveling to Earth, had indeed been bent by the sun's gravitational field, exactly as Einstein's equations had foretold. Overnight, Einstein became a global icon, and the world understood that mathematics could not only find hidden planets, but could also map the invisible curves and warps of the cosmos itself. How does it feel to know that a handful of symbols on a page can describe the bending of starlight and the architecture of a black hole? This was not an improvement on an old idea. It was a complete rewriting of the rules. Mathematics had graduated from predicting objects within the universe to predicting the very behavior of the universe's stage. If equations could so accurately describe a reality as counterintuitive as curved spacetime, what other impossible-seeming truths might they be holding, just waiting for us to solve for X? Einstein had reshaped the cosmos with his geometry of spacetime, but a new revolution was brewing in the subatomic realm. A brilliant and deeply reserved British physicist named Paul Dirac set out to unite the two great pillars of modern physics, quantum mechanics and special relativity. He believed the universe should be described by a single, elegant mathematical framework. In 1928, he succeeded, penning an equation of breathtaking simplicity and profound strangeness. The Dirac equation perfectly described the behavior of the electron, but it came with a bizarre and unsettling requirement. The math itself implied a symmetry, a kind of cosmic balance. For every solution that represented an electron, there was another mirror image solution. This twin would have the same mass as an electron, but it would carry a positive charge. Dirac had not set out to find a new particle, he had simply followed the logic of his symbols. The equations were speaking a truth he had not initially understood, pointing to a shadow world of antimatter. At first, he and others tried to interpret this mathematical ghost as the proton, but the numbers did not fit. The equation was insistent, it demanded a perfect mirror, a particle that was the electron's opposite in every way. Dirac later reflected that his equation seemed to be smarter than he was, possessing a knowledge of its own. It was a powerful admission. The mathematics was not just a tool. It was a guide to a reality no one had ever seen. Then, just 4 years later, the proof arrived from a cloud chamber. American physicist Carl Anderson was studying cosmic rays, high-energy particles raining down from space. In his photographs, he saw a track left by a particle with the exact mass of an electron, but curving in the opposite direction in a magnetic field. It was the positron, the antimatter twin Dirac's math had foretold. A new form of matter, predicted by pure reason, now had a physical signature. This discovery flung open a door to a hidden layer of reality. We now understand that empty space is not truly empty. At the tiniest scales, the vacuum of space is a seething quantum foam where particle-antiparticle pairs constantly flicker into and out of existence, borrowing energy from the void for an unimaginably brief moment. What does it mean that a line of symbols on a page could foresee an entire kingdom of matter? A mirror world that forms the very fabric of the vacuum itself. With Dirac's equation, mathematics ceased to be just a description of what we see. It became a gateway to particle realms that were, and remain, utterly beyond our direct senses. Dirac's equation had flung open a door to the quantum world, revealing antimatter and a seething vacuum. But this new landscape presented physicists with an even more baffling mystery. If the equations were so powerful, why did some particles have mass at all? According to the elegant framework known as the Standard Model of Particle Physics, particles like the W and Z bosons, which carry the weak nuclear force, should be massless, just like the photon. Yet experiment after experiment showed they were undeniably heavy. This was not a small inconsistency. It was a crack in the foundation of modern physics, threatening to bring the entire theoretical structure crashing down. Into this crisis stepped a quiet, unassuming theorist named Peter Higgs. He, along with several other physicists, turned to a branch of mathematics known as group theory, the study of symmetry. They proposed a breathtakingly elegant solution, a process called spontaneous symmetry breaking. Imagine a room filled with guests, all perfectly symmetrical in their arrangement. The moment one person decides to start a conversation with another, the symmetry is spontaneously broken and a preferred direction emerges. In the early universe, they theorized, a field now called the Higgs field permeated all of space, perfectly symmetrical. As the universe cooled, this symmetry broke, and the field settled into a new state, like a marble finally coming to rest at the bottom of a wine bottle. This new state was not one of zero energy. It was a kind of cosmic molasses that fills the vacuum of space. Particles that interact with this field, like the W and Z bosons, feel a kind of resistance as they move through it. This resistance is what we experience as mass. The mathematics was clear and insistent. This mechanism only worked if a certain particle existed, a quantum ripple in the Higgs field, the Higgs boson. For nearly 50 years, this particle was a ghost in the equations, a prediction born not from observation, but from pure mathematical necessity. The physicist Leon Lederman famously, and somewhat reluctantly, nicknamed it the God particle, not for any religious connotation, but to signify its profound, foundational role in granting mass to the universe. The hunt was on, a multi-billion-dollar quest to find a single particle that mathematics swore must be there. The search culminated deep underground, in a 17-mile ring straddling the French-Swiss border, the Large Hadron Collider. On July 4, 2012, scientists announced they had found it. The data revealed a tiny bump, a fleeting resonance that matched the precise signature the equations had foretold decades earlier. The Higgs boson was real. How staggering is it to realize that an abstract concept like symmetry, explored with pencil and paper, could dictate the construction of the most complex machine ever built, all to confirm a single, fundamental ingredient of reality. This was not a discovery made by accident, it was a verification, a cosmic checkmark placed beside a line of math that had been waiting patiently for its moment in the physical world. The equations that gave us mass also revealed a far more terrifying cosmic destiny. When a massive star exhausts its nuclear fuel, the outward push of radiation vanishes. With nothing to counter its own immense gravity, the star begins a fatal, irreversible collapse. It crushes itself down, smaller and smaller, denser and denser, until all its mass is compressed into an infinitely small, infinitely dense point, a singularity. For years, physicists like Einstein hoped this was a mathematical fluke, an artifact of the perfect symmetry in their models that would never occur in the messy real world. But in the 1960s, a mathematician named Roger Penrose, and later Stephen Hawking, proved this was not a fluke at all. Using the powerful tools of differential geometry and topology, they showed that singularities were an inevitable consequence of Einstein's own theory of gravity. Penrose introduced a brilliant concept called a trapped surface. Imagine a sphere of light rays, all pointing directly inward. In normal space, some of those rays would always escape. But within a collapsing star, a point of no return is reached where gravity becomes so intense that every single light ray, every possible path, is forced to converge inward. This is a trapped surface, and Penrose proved that its existence necessarily leads to a singularity, a place where the known laws of physics simply break down. The mathematics of geodesic incompleteness showed that within a black hole, the paths that particles and light rays follow, their world lines must simply end. They hit a boundary where space and time cease to have any meaning. Stephen Hawking later reflected that the math was so powerful and compelling that it forced physicists to accept black holes as real astrophysical objects, not just science fiction. The equations left no room for doubt. These monstrous entities had to exist. For decades, they remained shadowy predictions. Then, in April 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow at the heart of the galaxy M87. That glowing ring of light, silhouetted against the inky blackness of the event horizon, was a perfect match for the predictions of general relativity. It was a direct visual confirmation of an object whose existence was first carved out by pure mathematics. These cosmic vacuum cleaners, predicted by math long before any telescope could hope to see one, now shape our understanding of the universe. What does it say about the fabric of reality that a series of abstract symbols can dictate the existence of something so extreme, so powerful that it can trap light itself? The authority of mathematics over the cosmos had reached its absolute peak, proving that even the most violent and alien of phenomena are bound by the logic of numbers. Black holes represent the ultimate victory of gravity, a crushing finality predicted by mathematics. Yet those same equations, when applied to the universe's very first moments, suggest a story not of finality, but of infinite creation. Our entire cosmos, everything we can possibly observe, is likely the product of a microscopic quantum fluctuation that was then stretched to a macroscopic size by a violent, exponential growth spurt known as cosmic inflation. This theory elegantly solves several major puzzles in cosmology, but the mathematics of the inflationary field holds a far more radical secret. Under the right conditions, the process may be eternal. The driving energy field behind inflation does not shut off everywhere at once. Instead, it decays in localized patches, each one giving birth to a stable bubble universe like ours. Meanwhile, the inflating space between these bubbles continues to expand at an unfathomable rate, spawning an endless chain reaction of new bubbles. Each one is a self-contained cosmos, potentially with its own unique set of physical laws and constants. The mathematics of eternal inflation does not merely suggest a multiverse, it practically demands one. This idea finds a startling parallel in the abstract world of string theory. To unite gravity with quantum mechanics, string theory requires extra spatial dimensions. The mathematics describing how these dimensions curl up and stabilize points not to one unique solution, but to a colossal array of possibilities, a landscape of perhaps 10 to the 500 different vacuum states. Each point in this vast mathematical landscape corresponds to a universe with a different set of physical laws, a different value for the strength of gravity, or even a different number of fundamental forces. Physicist Max Tegmark takes this even further with his mathematical universe hypothesis. He proposes that our external physical reality is a mathematical structure. A radical corollary of this is that every mathematical structure that can exist does exist as a physical reality. The cosmos is not just described by math, it is math. Our universe is simply one particular mathematical structure that has self-aware substructures, us, within it. This framework provides a controversial yet mathematically coherent answer to a profound question: why is our universe so perfectly tuned for life? If the charge of the electron were slightly different, or the force of gravity slightly stronger, atoms and stars and life would be impossible. In a single universe, this seems like a miraculous coincidence. But in an infinite multiverse, where every possible set of physical parameters is realized somewhere, it is no surprise that we find ourselves in one of the rare bubbles where life can form. This is the anthropic principle. Imagine a boundless ocean of cosmic foam where each bubble is a universe with its own unique physics. In most, matter collapses instantly or flies apart. Stars never ignite, and complexity never arises. But in a tiny, precious fraction, the numbers align, and conscious beings emerge to gaze at the stars and wonder about their origin. The equations on our page are no longer just predicting hidden planets or particles. They are sketching the architecture of a reality so vast that our entire cosmos becomes a single grain of sand on an infinite beach. Could a version of you in another bubble be asking the very same question right now? The universe of the very small operates by a set of rules that defy all common sense. A single electron fired through a barrier with two slits does not go through one or the other. Instead, it behaves as if it passes through both openings simultaneously, creating an interference pattern of waves on the detection screen behind it. This is the double-slit experiment, and its result is a foundational mystery. The act of measuring which slit the electron goes through collapses this strange behavior, forcing it to act like a single particle. This wave-particle duality shattered the classical, deterministic universe. To make sense of this, physicist Erwin Schrödinger crafted an equation that did not describe the path of a particle, but the evolution of a mathematical abstraction, the wave function. This is not a wave of matter or energy, but a wave of probability. The wave function spreads out through space, and its peaks and troughs tell us the likelihood of finding a particle at any given location. It is a predictive map of potentialities, not a description of a single reality. This mathematical formalism led to a startling prediction: quantum tunneling. The equations showed that a particle, like an electron, has a finite probability of appearing on the other side of an energy barrier it classically should not be able to cross. It is not burrowing through, but rather, its probabilistic wave function extends through the wall, giving it a chance to manifest there. This is not a theoretical curiosity. It is the fundamental principle that makes modern electronics possible, allowing currents to flow in semiconductors. It is also a crucial mechanism inside stars, enabling protons to overcome their mutual repulsion and fuse, powering the sun and creating the elements of life. But what does the wave function actually represent? The dominant Copenhagen interpretation, championed by Niels Bohr, offers a pragmatic but philosophically dizzying answer. It states that the math does not describe a single objective reality, but only the probabilities of what we will observe upon measurement. The particle does not have a definite position until we look at it. The mathematics in this view is not a map of what is, but a catalog of what might be found. An even more radical idea emerged from the equations themselves, the many worlds interpretation. It takes the math at face value. If the wave function describes all possible outcomes, then all outcomes must occur. Every quantum decision, every random decay of an atom, causes the universe to branch into multiple copies, each one realizing a different possibility. In one world, the electron goes through the left slit, in another, the right. This interpretation suggests a multiverse of staggering proportions, born from the relentless logic of the Schrödinger equation. We are already harnessing this bizarre predictive power. Quantum computers leverage the property of superposition, where a quantum bit or qubit can be in a state of 0 and 1 simultaneously, just as the math dictates. This allows them to explore myriad computational paths at once, solving problems intractable for any classical machine. So we are left with a profound question. If our most fundamental mathematical description of matter insists that particles exist in a blur of multiple states and locations until observed, what does that say about the solidity of the world around us? The chair you are sitting on is mostly empty space, held together by quantum fields and forces whose behavior is governed by a set of probabilities. The mathematics of the quantum realm suggests that reality, at its core, is not a collection of definite things, but a tapestry of potentialities, waiting to be woven into experience by the act of interaction. The solid chair you sit on feels permanent, but the mathematics governing its atoms paints a far more fluid picture of time itself. We experience time as an unstoppable river flowing from past to future, yet the fundamental equations of physics, from Newton's laws to quantum mechanics, show a profound indifference to this direction. You can run the film of two colliding planets backward, and the math still works perfectly. So where does our relentless march forward come from? The answer lies not in the laws of motion, but in a statistical concept: entropy, described by the second law of thermodynamics. This mathematical principle states that the total disorder, or entropy, of an isolated system always increases. Imagine a new deck of cards, perfectly ordered by suit and value. Shuffle it just once, and that precise order is lost, replaced by randomness. The math does not forbid the cards from leaping back into their original sequence, but the probability is so vanishingly small it is effectively impossible. Entropy gives time its arrow. It explains why an ice cube melts in your drink but never spontaneously reforms, why memories are of the past and not the future. This mathematical law of increasing disorder is what writes the story of our lives in one direction only. Yet when we turn to Einstein's general relativity, the plot thickens. His equations for gravity allow for solutions known as closed time-like curves, paths through warped spacetime that loop back on themselves. In the intense gravity around a rotating black hole, for instance, the math permits a path where you could travel forward in time and return to your own past. The equations do not prohibit time travel, they provide a blueprint for it. This forces a deep philosophical question: is time real? Philosopher J.M.E. McTaggart argued that time is an illusion, a contradictory concept that cannot exist as a fundamental reality. Modern physicists like Carlo Rovelli echo this, suggesting that time does not flow at all. Instead, what we perceive as time may be an emergent property, a consequence of the quantum relationships between events. In this view, there is no universal clock ticking for the cosmos, only a network of changing connections from which the feeling of succession arises. The mathematics of cosmology pushes this even further, offering models of a cyclic universe. Our Big Bang may not have been a singular beginning, but merely one turn in an endless cycle of expansion and contraction. A cosmic heartbeat where the universe is reborn from the ashes of its own collapse, its timeline a loop with no start or finish. So we are left with a dizzying conflict between our senses and our symbols. Our lives are a movie reel we experience frame by frame, with entropy ensuring the story only makes sense when played forward. But the mathematics behind the projectors suggests the reel itself could be twisted into a circle, or that the frames themselves are the only reality, with the flow being a story we tell ourselves. Does time truly pass, or are we simply reading a cosmic clock that is not really there? The power of mathematics to challenge our most basic experience reveals that even the flow of time itself may be a prophecy written in the language of entropy and geometry. The quest to unite Einstein's gravity with the bizarre quantum world has led physicists down a path of breathtaking mathematical speculation. For decades, these two pillars of physics have refused to coexist peacefully, their equations breaking down when forced together. The most promising and controversial candidate for a theory of everything is string theory. Its core idea is radical. It replaces the point-like particles of traditional physics with unimaginably tiny, vibrating loops of energy, or strings. The different vibrations of a single string, like the harmonics of a violin, manifest as different particles, an electron, a quark, or a photon. But for the math of these vibrating strings to work, to produce a universe with gravity and the forces we observe, the equations make a non-negotiable demand. Space must have more than the three dimensions we experience. String theory requires extra spatial dimensions, curled up into shapes so small that a billion of them could fit inside a single atom. The properties of our entire universe, the number of particle families, the strength of forces, even the existence of life itself, are dictated by the specific geometry of these hidden dimensions. The mathematics points to a special class of intricate, multi-dimensional shapes known as Calabi-Yau manifolds. Picture a shape of such complex, twisted beauty that it can only be fully described in 6 or 7 dimensions. The way a string vibrates as it moves through the convoluted landscape of a Calabi-Yau manifold determines whether it acts like an electron or a neutrino. The physicist Ed Witten has spoken of the unexpected mathematical beauty that drives string theory forward, a powerful hint that we might be on the right track, even if experimental proof remains elusive. This framework opens up staggering possibilities such as the concept of brains, short for membranes. Our entire universe, with its 3 dimensions of space, could be a 3-dimensional brain, a mere slice floating within a much higher dimensional space, a bulk. Other brains, other parallel universes, could be floating just a minuscule distance away in these extra dimensions, completely invisible to us. To grasp this, think of a garden hose stretched across a field. From a distance, it looks like a simple one-dimensional line, but an ant crawling on its surface experiences a second dimension, the circular path around the hose's circumference. We are like creatures who can only perceive the long line, completely unaware of the hidden circular dimension curled up so tightly. The mathematics of string theory suggests our reality is precisely like that hose, but with 6 or 7 extra dimensions curled into a Calabi-Yau shape at every single point in space. So we are left with a profound question that challenges the very limits of our senses. What if everything you see, every star and every atom, is just a 3-dimensional shadow cast by vibrations in a higher dimensional reality? The equations provide the blueprint, insisting that the true nature of the cosmos is a symphony playing in 11 dimensions, while we are only hearing a single, haunting melody. The universe's grandest symphonies may be composed in hidden dimensions, but its most intimate melodies are written in the language of fractals. Look closely at a flake of snow, its crystalline arms branching into ever smaller, identical branches. Trace the ragged edge of a coastline on a map, where every bay reveals smaller inlets, and every inlet tiny coves, repeating the same irregular pattern down to the splash of a single wave. These are not random irregularities, they are fractal patterns, and they reveal a geometry far richer than the perfect circles and triangles of our schoolbooks. The mathematician Benoit Mandelbrot asked a deceptively simple question: how long is the coast of Britain? The answer, he found, depends entirely on the length of your ruler. Measure with a satellite and you get one number. Walk the coast with a yardstick, counting every tiny rock and crevice, and the length grows immensely. Use a microscope on every grain of sand, and the length becomes infinite. This was the birth of fractal geometry, a new mathematics to describe the rough, fragmented, and infinitely complex shapes of the real world. Mandelbrot famously declared that clouds are not spheres, mountains are not cones, and coastlines are not circles. Nature's complexity demanded a new kind of math. At the heart of this is a process of breathtaking simplicity and power: iteration. A single, simple equation is fed back into itself over and over again, in a loop of recursion. From this repetitive feedback erupts an unending cascade of complexity, a universe of detail emerging from a seed of pure logic. The most famous of these is the Mandelbrot set, a single equation plotted on a complex plane. Zoom into its boundary, an infinitely long, squiggly line, and you do not reach a smooth curve. Instead, you find the original shape again and again and again, with endless variations spiraling into eternity. It is a mathematical universe where every zoom level reveals a new world, a new set of spirals and seahorse tails, all encoded in the original, simple rule. This is not just an abstract marvel, it is the very blueprint of our world. A fern frond perfectly demonstrates this self-similarity. Each tiny leaflet is a miniature copy of the whole branch, which is itself a copy of the entire fern. Your circulatory system is a fractal, with arteries branching into arterioles, then into capillaries, a pattern optimized to reach every cell in your body with maximum efficiency. The same branching pattern appears in the lightning bolt, the river delta, and the structure of a tree. Scientists now use fractal math to model the chaotic swirl of weather systems, to understand the distribution of galaxies in the cosmos, and to map the tangled pathways of neurons in your brain. This mirroring between a simple iterative equation and the structure of a lung or a galaxy forces a profound question upon us. Does the overwhelming prevalence of fractals in nature mean the universe is not just described by mathematics, but is fundamentally built from its recursive, self-similar logic? The fern and the Mandelbrot set seem to be made from the same cosmic cloth, one physical, the other pure idea, yet both singing the same geometric song. Edward Lorenz was simply trying to model weather patterns on his computer in the 1960s, a task that should have been straightforward. One day, he decided to rerun a simulation, but to save time, he entered the initial conditions not from the full printout, but from an earlier, rounded-off number in the sequence. He expected the computer to reproduce the previous weather pattern. Instead, it generated a completely different forecast. This tiny, almost negligible rounding error, a difference of less than 1 part in 1,000, had completely diverged from the original path. Lorenz had stumbled upon a profound truth, that in certain systems, the slightest variation in starting conditions can amplify exponentially over time, leading to wildly different outcomes. He poetically named this the butterfly effect, suggesting that the flapping of a butterfly's wings in Brazil could set off a chain of events that might ultimately cause a tornado in Texas weeks later. The weather was not random, it was chaotic. The mathematics behind this revelation is known as nonlinear dynamics, which studies systems where the output is not directly proportional to the input. Small causes can have enormous, unforeseeable effects. To visualize these systems, mathematicians use a concept called a strange attractor. Picture a shape in an abstract space, a phase space, where every point represents a possible state of the system. A chaotic system, like the weather, will never settle into a repeating cycle, but its path through this phase space is not random. It is drawn to a specific, infinitely complex fractal shape. This is the strange attractor, a portrait of order within the chaos, a mathematical guarantee that while the system's path is unpredictable, it is forever bound within a hidden, beautiful structure. We can measure this inherent unpredictability using Lyapunov exponents, numbers that tell us how quickly two nearly identical starting points in a system will diverge from one another. A positive Lyapunov exponent is the hallmark of chaos, a mathematical confirmation that tiny errors will grow, and that long-term prediction is fundamentally impossible, not due to a lack of data, but due to the very nature of the system itself. You can see this play out in a simple, mesmerizing physical object, the double pendulum. Its motion is governed by straightforward equations of motion, a completely deterministic system. Yet when you set it swinging, its movement is a wild, erratic dance, flailing in a seemingly random frenzy. Two trials started with imperceptibly different pushes will quickly evolve into entirely different patterns. The equations perfectly describe its motion, but they cannot long predict its precise path, a perfect illustration of deterministic chaos. This mathematics of the unpredictable is everywhere. The long-term stability of our solar system, while generally stable, contains chaotic elements that make precise predictions over millions of years impossible. The fluctuations of the stock market, the drip of a faucet, the firing of neurons in your brain, all exhibit this blend of deterministic rules and practical unpredictability. So we are left with a powerful and humbling thought. If mathematics can so elegantly model the chaotic whirl of a storm or the flailing of a pendulum, does this mean that what we call randomness is merely a veil for a deeper, hidden structure we have not yet fully mapped? Chaos theory reveals that the universe is not a rigid clockwork, but a dynamic, sensitive, and infinitely complex system where predictability and surprise are woven together by the same mathematical threads. Chaos theory shows us a universe of exquisite sensitivity, where tiny changes blossom into vast, unpredictable outcomes. Yet this same mathematical lens is now being trained on the most unpredictable system of all, the human mind itself. We arrive at the hard problem of consciousness, a mystery that has haunted philosophers and scientists for centuries. Why should the intricate firing of billions of neurons in your brain produce the rich, inner world of your experience, the taste of chocolate, the feeling of awe, the color red? Physical processes are one thing, but subjective feeling is another. How does matter light up with mind? A radical answer is emerging, not from philosophy alone, but from mathematics. Integrated information theory, developed by neuroscientist Giulio Tononi, proposes a bold framework. It suggests that consciousness is not a magical emergent property, but a fundamental, measurable quantity that arises from the specific structure of a system's causal power. In essence, consciousness corresponds to a system's ability to influence itself, to have a rich repertoire of internal states that are integrated into a unified whole. The theory represents this with a single Greek letter, phi, a number that quantifies the degree of consciousness. A high phi value indicates a highly integrated system with a vast amount of intrinsic information, like a human brain. A low phi value might correspond to a simpler system. The mathematics used draws from information theory and topology, mapping the causal relationships within a network. It seeks to identify the specific structure, the shape of information flow, that generates a subjective perspective. Giulio Tononi has stated that consciousness is a fundamental property possessed by physical systems having a specific causal structure, and that this structure is what matters. This leads to some deeply controversial implications. If consciousness is truly a matter of mathematical structure, then it is not exclusive to biological brains. According to the theory, any system with a sufficiently high phi could be conscious. This includes sophisticated future artificial intelligences, but it also points toward a view called panpsychism, the idea that consciousness is a universal property of matter. In this view, even a simple system like a thermostat or a single-celled organism might possess a minuscule, perhaps unfathomable, amount of conscious experience. Think of it like a computer's processing capacity. A basic calculator can run a simple program, while a supercomputer can host a vast, immersive virtual reality. Both are computers, but their capacity for complexity is vastly different. Consciousness, in this mathematical view, might be akin to the most complex program of all, one that requires a system with a highly integrated and differentiated causal architecture to run. So we are left with a question that challenges the core of our identity. If the flicker of awareness within you can be modeled by an equation and assigned a number, what does that mean for the nature of reality itself? Could a sufficiently advanced artificial intelligence, built upon the right mathematical principles of information integration, ever look out at the world and genuinely feel that it is there? This inquiry bridges the abstract world of numbers to the most intimate truth we know, our own inner light. A simple circle drawn in sand holds a secret known to every corner of the cosmos. The ratio of its circumference to its diameter, the number pi, appears not just in geometry, but in the statistical equations describing the distribution of stars and in the ripples of a gravitational wave. This is not an isolated case. Scattered throughout the laws of physics are other fundamental constants, pure numbers that seem to be baked into the very fabric of reality. They are the universe's fixed points, its immutable settings. The fine structure constant, approximately 1/137, governs the strength of the electromagnetic force. Its value dictates how atoms hold together, how light interacts with matter, and the very process of nuclear fusion inside stars. If this number were just a few percent different, carbon-based life would be impossible, and the universe would be a sea of inert hydrogen or a chaos of rapidly collapsing matter. Then there is Euler's number E, the base of the natural logarithm. It emerges inevitably from the mathematics of growth and decay. It describes the unchecked spread of a virus, the cooling of a cup of coffee, and the radioactive decay of an atomic nucleus. Its ubiquity in calculus hints at a deep, underlying pattern in the way change itself operates throughout nature. The physicist Paul Dirac was deeply fascinated by these cosmic numbers. He noticed a strange and seemingly coincidental relationship between the constants governing the vast cosmos and those ruling the tiny quantum world, leading him to propose the large numbers hypothesis. He wondered if these enormous, dimensionless numbers were connected, a clue that the constants might not be fixed forever, but could change over the lifetime of the universe. This idea, while not widely accepted today, underscores the profound mystery. Why do these constants have the exact values they do? The mathematics itself cannot derive them, it can only incorporate them as foundational inputs. This leads to the anthropic principle, a compelling, if controversial, explanation. In a multiverse of infinite bubbles, each with its own random set of physical constants, only in the rare bubbles where the numbers align with exquisite precision can stars shine, planets form, and conscious beings arise to ponder the very numbers that allow them to exist. We are living proof of a universe whose mathematical settings are just right. Even the golden ratio, approximately 1.618, appears with curious frequency in nature's designs, from the spiral of a nautilus shell to the arrangement of seeds in a sunflower, a pattern that can be generated by a simple iterative mathematical sequence. So are these constants merely a set of coincidences, a cosmic roll of the dice that happen to land in our favor? Or is their pervasive, precise presence the ultimate evidence that we inhabit a universe not just described by mathematics, but one that is, at its heart, a mathematical structure itself? The numbers are speaking. The question is, what are they trying to tell us? Even the most perfect logical system contains a whisper of its own limitations. In 1931, a quiet logician named Kurt Gödel published a paper that sent shockwaves through the very foundations of mathematics. His incompleteness theorems were not just another discovery, they were a profound meta-statement about the nature of truth itself. Gödel demonstrated, with ironclad logical precision, that any consistent formal system complex enough to describe basic arithmetic is necessarily incomplete. This means there will always be true statements within that system that cannot be proven using the rules of the system itself. Think of it as a mathematical constitution that is so comprehensive, it guarantees the existence of citizens it cannot govern. Gödel achieved this by constructing a statement that essentially said, "This statement is not provable. If you could prove it, you would prove it false, creating a contradiction. If you cannot prove it, then it is true but unprovable. The system is either inconsistent or incomplete." Mathematics, the very language we use to predict reality, was shown to have a fundamental blind spot. Gödel himself was a mathematical Platonist, believing that mathematical truths exist in an abstract realm independently of human minds. His theorems, for him, were not a failure of mathematics, but proof that this realm of truth is richer than any single set of rules we can devise to capture it. The implications ripple outward into physics. If our most powerful formal systems are inherently incomplete, what does that mean for a so-called theory of everything? Such a theory would be a finite set of equations and rules, a formal system intended to describe all physical reality. Gödel's work suggests that even if we found it, there would be truths about the universe that the theory could not prove or predict. It would be like a map that is perfectly accurate for every landmark we can visit, yet is fundamentally incapable of marking every possible point of interest in the territory. The universe may contain phenomena that are real and consistent with the laws of physics, but whose existence or properties are logically undecidable from within those very laws. This places a fundamental limit on prediction. We can ask questions about the cosmos that are perfectly meaningful, yet forever beyond the reach of a final, complete mathematical answer. Does this mean reality itself is inherently incomplete? Or simply that our magnificent tool for describing it has a built-in horizon beyond which it cannot see? Gödel's theorems sketch the horizon of our mathematical knowledge. But what if that horizon is not a feature of reality, but of the system rendering it? The philosopher Nick Bostrom proposed a startling trilemma, a set of three possibilities, one of which is almost certainly true. Either advanced civilizations never reach the technological stage capable of running detailed ancestor simulations, or they choose not to, or we are almost certainly living in one such simulation right now. The logic is mathematical, a simple matter of statistics. If even a tiny fraction of advanced civilizations run a large number of high-fidelity simulations of their own history, the number of simulated minds would vastly outnumber the base reality minds. Therefore, if such simulations are possible at all, any randomly selected conscious being, like you, is far more likely to be one of the simulated ones. This is the simulation hypothesis, and it finds eerie echoes in the very laws of physics we have explored. Look at the pixelated nature of reality at the smallest scales. Quantum mechanics reveals a universe that is not continuous, but quantized. Energy, momentum, and angular momentum come in discrete, indivisible packets, much like the bits in a digital computer. There is a fundamental limit to how fast information can travel, the speed of light, acting as a processing speed limit for the cosmos. Even the smooth fabric of spacetime may break down at the Planck scale into a granular foam, a kind of cosmic resolution limit. The entrepreneur Elon Musk has bluntly stated that the odds we are in base reality are 1 in billions. Precisely because the progression of video games from Pong to photorealistic virtual realities in just 40 years points to a future of indistinguishable simulations. But this idea is more than a thought experiment. It is being explored with the tools of information theory and complexity mathematics. Some physicists, like John Archibald Wheeler, suggested the universe might be fundamentally informational, with his famous slogan, "It from bit." Could our cosmos be a vast cellular automaton, akin to Conway's game of life, but operating on a three-dimensional grid at the Planck scale? In such a system, incredibly complex structures, from galaxies to conscious beings, could emerge from the iterative application of a few simple, underlying rules, just as gliders and complex patterns emerge from the four basic rules of the game of life. The mathematical laws we have discovered, from the wave function to general relativity, would not be fundamental, but rather the emergent, high-level description of this underlying computational process. So we are left with the most disorienting question of all. If our most powerful tool for understanding reality, mathematics, points so compellingly toward a universe built from information and computation, does that make the equations we uncover not laws of nature, but simply the source code we are beginning to read? The solidity of the world around you, the feeling of the sun on your skin, the vastness of the night sky, all of it could be the magnificent output of an unfathomable calculation running somewhere else. The ultimate predictive power of mathematics now confronts its greatest challenge, the origin of everything from nothing. The Big Bang theory describes a universe exploding from an infinitely hot, dense point, but it leaves a profound question unanswered. What set that initial condition in motion? To answer this, physicists turn to quantum cosmology, applying the strange rules of the quantum world to the entire cosmos. One of the most compelling ideas is the Hartle-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking. In this model, the universe has no initial boundary in time, no singular point of creation. Instead, the mathematics uses a concept called imaginary time, a mathematical tool that transforms the beginning of the universe. If we think of real time as a vertical line with a definitive starting point at the Big Bang, imaginary time turns that point into a smooth, curved surface, like the south pole of a globe. There is no sharp edge, no moment of nothingness before which time did not exist. The universe simply is in a self-contained, finite geometry. This is described using Euclidean geometry, the geometry of flat space, which allows for this smooth, closed surface. The proposal provides a wave function for the universe, a mathematical entity that describes the probability of the entire cosmos having a certain initial configuration, including the rapid inflationary expansion that followed. Hawking famously suggested that if we find the answer to why the universe exists, we would know the mind of God, a poetic way of saying we would grasp the ultimate, logical foundation of all reality. To visualize this spontaneous emergence, think of the quantum vacuum, which we know is not truly empty. Particle-antiparticle pairs constantly flicker into existence. Now, scale that idea up cosmically. The universe itself could be a quantum fluctuation, a bubble of spacetime that spontaneously nucleated from nothing, stabilized by its own laws, and then inflated to a macroscopic size. The math describes a probability, however small, for this to occur. So we are left with a staggering implication. The equations suggest that the universe could have come into existence without a cause, without a creator, simply as a consequence of mathematical and quantum logical necessity. Does this mean that the question of why there is something rather than nothing is ultimately a mathematical one? The quest to use numbers to narrate our own genesis pushes this prophetic language to its absolute limit, asking it to write the first chapter of existence itself. A spiral galaxy should slow its spin the farther you look from its bright center. The outer stars, feeling a weaker gravitational pull, ought to drift along at a leisurely pace compared to the inner core. This is the simple, predictable dance demanded by Newton's laws and the gravity of visible matter. But in the 1970s, astronomer Vera Rubin, studying the rotation of the Andromeda Galaxy, found something deeply unsettling. The stars at the edge were not slowing down. They were racing around just as fast as those near the center. It was as if the outstretched arms of a spinning ice skater moved just as quickly as her body, defying all logic. Rubin's meticulous data presented an inescapable conclusion. Either our fundamental understanding of gravity was wrong, or there was something else out there. A vast halo of unseen matter whose gravity was whipping those outer stars to incredible speeds. The universe, it seemed, was mostly made of something we could not see. Vera Rubin herself remarked that the discrepancy was so large and so consistent that it left no viable alternative. The stars were telling us a story our eyes could not read. The equations of general relativity provided the mathematical lens to see this invisible actor. By mapping the gravitational distortions, the way this unseen mass bent the light from distant galaxies in a phenomenon called gravitational lensing, cosmologists could trace its ghostly outline. The math inferred a cosmic scaffold, a web of dark matter upon which the luminous galaxies are merely strung like dewdrops on a spider's web. Then came a second, even more profound shock. In the late 1990s, two independent teams studying distant supernovae made a discovery that earned them a Nobel Prize. They found that the expansion of the universe was not slowing down due to gravity, as everyone expected. It was speeding up. Something was forcefully pushing the cosmos apart, an anti-gravity effect woven into the fabric of space itself. Einstein's equations of general relativity contained a term for just such a repulsive force, a cosmological constant he had once called his greatest blunder. The math had been there all along, waiting for the data to give it meaning. This mysterious driver was named dark energy. The numbers that have emerged from these mathematical deductions are staggering. All the stars, planets, and galaxies we see with every telescope amount to less than 5% of the universe. Dark matter, this invisible gravitational glue, makes up about 27%. And dark energy, the force accelerating the expansion of everything, dominates at a colossal 68%. We are living in a cosmos where 95% of its content is completely invisible and intangible to us, known only through the prophetic authority of mathematics. It is a humbling thought. The very ground beneath your feet, the air you breathe, the screen you are watching, all of it is the rarest of cosmic phenomena. We are made of the 5%. So what does it say about reality that its dominant components are completely hidden from our senses, yet are laid bare by the language of numbers? Mathematics has become our sixth sense, a cosmic detective that sees the invisible mass shaping galaxies and feels the repulsive energy stretching the void between them. The spiral of a nautilus shell and the branching of a tree are not just beautiful accidents. They are the visible signatures of a mathematical order that governs every living thing. From the double helix of your DNA to the complex dance of an entire ecosystem, biology is saturated with patterns that can be described, and even predicted, by numbers. This connection was championed by the biologist D.R.C. Thompson in his groundbreaking work, On Growth and Form. He argued that the shapes of animals and plants are not merely a product of evolution's random tinkering, but are also constrained and guided by physical laws and mathematical principles. The hexagonal cells of a honeycomb, for instance, are not a clever design choice by bees, but the inevitable result of physics, the most efficient way to partition a surface into equal areas with the least amount of wall. Thompson showed how the skulls of different animals could be transformed from one to another through simple geometric deformations, as if nature was working from a shared mathematical blueprint. This mathematical lens allows us to model the very engine of life, evolution itself. Population genetics uses a set of elegant equations to predict how the frequency of genes will change in a population over time. The Hardy-Weinberg principle provides a mathematical baseline, a model of a population where no evolution is occurring. When real-world data deviates from this model, the equations point directly to the forces at work, whether it is natural selection, genetic drift, or mutation. We can write differential equations that capture the oscillating dance of predator and prey, the fox and the rabbit populations rising and falling in a perpetual, predictable rhythm. The same mathematical tools now map the firing of neurons in your brain, with neural networks modeling how learning emerges from the weighted connections between cells. Perhaps the most striking examples are found in the very structures of life. The Fibonacci sequence, where each number is the sum of the two preceding it, appears with uncanny regularity. Look at the spirals of a sunflower. The seeds are arranged in intersecting spirals, and if you count them, you will find the numbers are almost always adjacent Fibonacci numbers, like 34 and 55. This specific arrangement is mathematically optimal for packing the most seeds into the flower's head. The same spiral unfolds in the chambers of a nautilus shell, a perfect logarithmic spiral that echoes the growth pattern encoded in its genes. This predictive power extends to our own lives. Statistics and probability allow us to calculate the risk of inherited genetic disorders, to track the spread of a virus through a population, and to model the trajectory of a pandemic with stunning accuracy. The same equations that describe the diffusion of a drop of ink in water can model the spread of a beneficial gene through a species or the foraging pattern of a slime mold. So we are forced to ask a profound question. If mathematics can so perfectly map the growth of a leaf, the pulse of an ecosystem, and the code of our own heredity, does this mean life itself is a mathematical phenomenon? Are we, and every living thing, intricate expressions of a deeper numerical reality, evolving according to rules written in the silent language of geometry and number? The ancient Greeks studied prime numbers as objects of pure mathematical beauty, never suspecting these indivisible integers would one day become the bedrock of global security. For centuries, secret messages relied on simple ciphers, but the digital age demanded a far more powerful lock, one that could be openly distributed yet remain unbreakable. The answer emerged from the abstract world of number theory, turning a puzzle that had fascinated mathematicians for millennia into a practical shield for our most private information. This is the story of RSA encryption, a system that protects your online transactions and messages. It works because of a clever mathematical asymmetry involving prime numbers. Multiplying two large prime numbers together is a trivial task for any computer, but reversing the process, taking that enormous product and figuring out which two primes were used to create it, is phenomenally difficult. This problem, known as prime factorization, is the one-way mathematical lock at the heart of modern cryptography. The security of your data does not rely on the encryption algorithm being secret, but on the sheer computational infeasibility of undoing the multiplication. As one cryptographer noted, we are in an eternal race, where the mathematical difficulty of breaking a code must always stay ahead of the advancing power of computers. This race is quantified using modular arithmetic, often called clock math. Imagine a clock face with only the numbers 0 through 11. If it is 10 o'clock and you add 4 hours, you arrive not at 14, but at 2 o'clock. This wrapping around is the essence of modular arithmetic, and it creates mathematical functions that are easy to compute in one direction, but incredibly hard to reverse without a special key. The entire system is a mathematical prediction, a confident forecast that certain problems will remain too hard to solve for decades, thus guaranteeing the privacy of our digital lives. Yet this prediction is now being tested by a new kind of mathematics, Quantum cryptography uses the principles of quantum mechanics, like the observer effect, to create a theoretically unbreakable key. If a hacker tries to eavesdrop on a quantum key exchange, their very act of measurement will disturb the quantum states, instantly revealing their presence. This is not a harder mathematical problem. It is a different kind of security altogether, based on the fundamental laws of physics. Think of it as a lock that is effortless to close but snaps shut and alerts the owner the moment anyone tries to pick it. The math that once predicted hidden planets now predicts the future integrity of our digital world. How does this abstract realm of number theory protect your privacy every time you send a message or make a purchase? It is a prophetic use of mathematics that actively builds and safeguards the virtual realities we increasingly inhabit, ensuring that some secrets remain mathematically destined to stay that way. Symmetry is nature's favorite language, spoken in the perfect six-fold pattern of a snowflake and the majestic spiral arms of a galaxy. This deep-seated love for balance is not merely aesthetic. It is the foundational principle from which the fundamental forces of the universe emerge. To decipher this cosmic code, physicists turn to a branch of mathematics known as group theory, the formal language of symmetry. It allows us to categorize symmetrical transformations, like rotating a square or swapping identical particles, and in doing so, it predicted the very forces that govern reality. At the heart of this lies a profound connection discovered by mathematician Emmy Noether. Her revolutionary theorem established that for every continuous symmetry in nature, there is a corresponding conservation law. The symmetry of time translation, the fact that the laws of physics are the same today as they were yesterday, directly implies the conservation of energy. The symmetry of rotational invariance leads to the conservation of angular momentum. Noether showed us that the beautiful patterns we see are not just decorative, they are the source of the universe's most enduring rules. This mathematical insight paved the way for one of the greatest triumphs of theoretical physics, the unification of electromagnetism with the weak nuclear force. Through a concept called gauge symmetry, physicists like Sheldon Glashow, Abdus Salam, and Steven Weinberg constructed a single, elegant framework. Think of gauge symmetry as the requirement that the laws of physics must remain unchanged under certain local transformations, much like a perfectly balanced mobile remains stable no matter how you gently twist its individual components. The mathematics dictated that this unified electroweak force must be mediated by four particles: the familiar photon and a trio of then undiscovered particles, the W+, W-, and Z bosons. The equations foretold their masses and their behaviors with stunning precision. When these particles were later discovered in particle accelerators, exactly as predicted, it was a resounding victory for symmetry as a prophetic guide. The quest did not stop there. The same mathematical principles are now being used in the ambitious drive toward a grand unified theory, a single symmetric framework that would merge the electroweak force with the strong nuclear force. The equations suggest that at the incredibly high energies of the early universe, these three forces were one, a perfect symmetry that broke as the cosmos cooled. Could the universe's deepest truths, from the spin of an electron to the explosion of a supernova, all be encoded in these symmetrical patterns? This forecasting reveals mathematics not just as a tool for calculation, but as the ultimate unifying principle, a lens through which the fragmented pieces of reality are seen as one coherent and beautiful whole. Will the cosmos end in ice, fire, or a violent tear? The answer is not written in the stars, but in a set of equations scribbled on a page. From Einstein's theory of general relativity, a Russian physicist named Alexander Friedmann derived a set of mathematical relationships now known as the Friedmann equations. These deceptively simple formulas act as the universe's birth certificate and its death warrant, all in one. They describe cosmic evolution by balancing the expansion energy from the Big Bang against the gravitational pull of all the matter and energy within the cosmos. The outcome hinges on a critical density parameter, a single number that determines the ultimate fate of everything. If the average density of the universe is too high, gravity will eventually win, reversing the expansion in a cataclysmic Big Crunch, a fiery collapse back into a singularity. If the density is too low, the universe will expand forever, its galaxies growing ever colder and more distant in a slow, dark Big Freeze. And then there is the third, more terrifying option dictated by the nature of dark energy. If this repulsive force strengthens over time, it could overcome all binding forces, not just expanding the universe but stretching the very fabric of spacetime itself. In this Big Rip scenario, galaxies, stars, planets, and even atoms would be torn apart in a final, violent moment of dissolution. Cosmologists like Saul Perlmutter, who helped discover the accelerating expansion, have described the process as using distant supernovae as cosmic mileposts, measuring their dimming light to chart the universe's expansion history with mathematical precision. This data is then cross-referenced with the faint afterglow of the Big Bang, the cosmic microwave background. This ancient light, a snapshot of the infant universe, serves as a rigorous test for the Friedmann equations, confirming their predictions about the geometry and composition of the cosmos. To grasp these cosmic destinies, picture throwing a ball straight up from the surface of the Earth. The ball's fate depends entirely on its initial speed. Throw it too slowly and gravity pulls it back down, a Big Crunch. Throw it at exactly escape velocity and it slows to a stop at infinity, a balanced, flat universe. Throw it even faster and it never looks back, a perpetual expansion. Our universe is that ball, and the Friedmann equations are the physicist's calculation of its launch. Does knowing that the entire cosmic story, from the first flash to the final darkness, can be captured in a handful of mathematical symbols, change how you see your own brief, brilliant moment within it? This is the ultimate predictive scope of mathematics, a language that can narrate the entire lifespan of reality. Your experience of the world is a carefully constructed illusion. Your brain does not simply receive a raw feed from your eyes and ears. Instead, it constantly generates predictions about what you should be seeing and hearing, using a form of probabilistic mathematics known as Bayesian inference. This is the core of the Bayesian brain theory. Your mind is like a brilliant detective at a crime scene, never possessing all the facts, but instead piecing together fragmented clues, prior experiences, and statistical likelihoods to build the most plausible story of what is happening right now. The sensory data from your nerves are just the clues, but the narrative of your reality is the brain's best guess. This mathematical process explains why we are so easily fooled by optical illusions. In the famous checker shadow illusion, two squares of identical shade appear dramatically different because your brain's model of the world, built from a lifetime of experience, insists that a shadow darkens colors. It overrides the raw data with its mathematically calculated prediction of what the color should be. Neuroscientist Carl Friston formalized this idea with his free energy principle, which proposes that the brain's fundamental drive is to minimize surprise or prediction error. It relentlessly fine-tunes its internal model of the world to better match the incoming sensory stream. This mathematical imperative to reduce uncertainty even predicts our cognitive biases. Confirmation bias, for instance, is our brain's tendency to favor sensory information that confirms its existing predictions, making it easier to maintain a stable, low-energy model of reality. This same Bayesian mathematics now powers the most advanced artificial intelligence. Machine learning systems that can recognize a face or navigate a city street are doing precisely what your brain does. They are using statistical models to predict patterns from noisy data, learning to see by constantly testing and updating their predictions about the world. So we are left with a deeply personal question. If your perception is not a direct window to the world, but a statistical inference generated by a 3-pound organ inside your skull, then what are you truly experiencing? The solidity of the table, the color of the sky, even the meaning of these words, all of it is a mathematical best guess. This revelation blurs the line beyond recognition, suggesting that the outer world and your inner computation are not two separate things, but parts of a single, intertwined process of prediction. Alan Turing sat down with pencil and paper and imagined a machine of breathtaking simplicity. It consisted of an infinite tape, a head that could read and write symbols, and a set of basic instructions. This abstract conception, the Turing machine, was not meant to be built, but to think with. It was a mathematical archetype for computation itself. From this elegant foundation arose a profound idea, the Church-Turing thesis. This is not a proven theorem, but a powerful assertion about the very nature of calculation. It states that any function which can be computed by a systematic procedure can be computed by a Turing machine. This mathematical definition draws a line in the sand of logic, separating the possible from the impossible. It predicts with certainty which problems can be solved by any algorithm, no matter how powerful the future computer. And it reveals problems that are fundamentally unsolvable. The most famous of these is the halting problem. Can we write a program that will analyze any other program and its input, and correctly determine whether that program will ever finish running or loop forever? Turing's mathematics delivered a resounding no. Such a universal analyzer is logically impossible. This was not a limitation of engineering, but a fundamental barrier woven into the fabric of logic itself. Turing himself saw the deeper implications for intelligence, pondering whether a machine could ever think. He suggested that we might one day speak of machines thinking without expecting to be contradicted, a prediction that now echoes through every conversation about artificial intelligence. This mathematical framework of computability has stunning implications for physics. If the universe operates on a set of finite, discrete rules, then the Church-Turing thesis suggests that the entire cosmos might be computable. Its evolution, from the Big Bang to the formation of galaxies, could be the output of a vast calculation. We can see a miniature version of this in cellular automata, like Conway's game of life. A grid of cells, each either on or off, follows a handful of simple rules about neighbors. From this stark simplicity, gliders emerge, complex patterns replicate and travel, and entire ecosystems of logic blossom into existence. The universe, in this view, could be a cosmic cellular automaton running on a lattice at the Planck scale. The laws of physics we have discovered, from quantum mechanics to general relativity, would then be the high-level, emergent description of this underlying computational process. So we are faced with a question that reaches to the core of existence. If the universe is computable, if its every event can be simulated by a sufficiently powerful Turing machine, does this mean that everything we are and everything we see is just mathematics in motion? The equations are no longer just predicting objects or forces. They are predicting the nature of process itself, defining the very idea of what can and cannot happen in reality. The algorithms that predict your next online purchase are now learning to predict the formation of new molecules. Machine learning systems, built on layers of statistical mathematics, ingest colossal datasets, discerning subtle patterns invisible to the human eye. Demis Hassabis of DeepMind has described this as using artificial intelligence as a microscope for complexity, allowing us to navigate problems that were previously too vast or intricate. These neural networks are not programmed with explicit rules. Instead, they train on millions of examples, their internal mathematical models growing increasingly accurate at forecasting everything from protein folding to next week's weather. This is prediction on a scale we have never seen, where the model itself becomes a kind of oracle. its predictions shaping the development of new medicines and materials. Yet this is only one half of the coming revolution. While classical computers, even powerful ones, hit a fundamental wall with certain problems, a new kind of machine is emerging from the very equations that once foretold antimatter. Quantum computing harnesses the bizarre principles of superposition and entanglement, allowing a quantum bit or qubit to exist in multiple states at once. Where a classical computer must check possibilities one by one, a quantum computer can explore a near-infinite number of paths simultaneously. This is not merely a faster calculator. It is a different way of processing reality itself, one that was first glimpsed in the abstract mathematics of the quantum realm. The greatest challenge now is not building the hardware, but writing the software, developing new quantum algorithms that can outperform their classical counterparts for tasks like simulating complex chemical reactions or cracking the cryptographic codes that currently protect our digital world. Think of this entire endeavor as polishing a cosmic crystal ball. Each advance in our mathematical models and each leap in computational power wipes away another layer of obscurity, offering a clearer vision into the hidden workings of nature. We are on the cusp of using these tools to run perfect simulations of entire biological processes inside a living cell, or to model the birth of a galaxy with such fidelity that we could step inside and watch it form. What entirely new states of matter, what unseen cosmic structures, might be revealed when our predictive power is no longer limited by the slow, sequential logic of classical machines. This new frontier, built on the twin pillars of artificial intelligence and quantum computation, promises to extend mathematics' prophetic voice into realms we cannot yet even frame as questions.